PMSM Permanent Magnet Synchronous Motor works. So you can see when I give a current through the A phase, I'll get direction like this phase. So this is a frame of reference. So we'll convert stationary frame, will go to a rotating frame that will rotate with the this. So this is the stationary frames. I'll have a rotating frame. So this is theta. Theta will be equal to omega into t, where omega is the rotation speed of rotation of this. So why we do this is the currents, all the quantities that we observe in the stationary frame will be sinusoidal. So if I convert this, it will be equivalent of saying all the quantities in this will be constant DC, because they are also rotating. So that's the, so if this will become a DC quantity, or any current in these three frames will come out as a DC current in D and Q axis, D and Q reference. So that's it. So you can work it out. It's a, this is 120. In these, you have to add components in or either balance components. So from that you'll get so this, you'll get a matrix like this, and you can write so these are all instantaneous values. For at any instant, if you plug values of current in A phase, B phase, C phase, you'll get this ID, IQ and IQ. So ID, IQ will be along this, and IQ will be a axis that is coming up. It basically represents the amount of unbalance in the current. So if you give balanced three-phase supply, I0 will be 0 at all instants. So this is this. Then this constant root of 2 by 3 is there, so that power in instantaneous power in both the frames come out to be same. So instantaneous power in ABC frame will be this, and in, so if I apply transformation to this and I find power, so P dq will be coming out as 3 by 2 times so this is what I get in the dq reference. So that these two come out to be equal, I have to keep this constant root of 2 by 3 here. So when I do the transformation, I'll get these. So for a permanent magnet synchronous motor, in each phase I can write Faraday's law. So VA will be equal to IA LA plus IB into M plus IC into M plus this, the flux due to the magnet. That will be some lambda MA. Similarly, VB will come out IALB IA into M plus IB into L plus IC into M plus lambda MB, and so on. So when I apply the transformation to these equations, eventually what I get is VD VQ is equal to so this d by dt because that flux linkage. So after, if I apply the transformation to both the voltages, I'll get VD equal to lambda d q is equal to lambda d id ld plus lambda m, where lambda m is the flux of the magnet. So on applying the transformation, you get these equations. So power is this P dq into 3 by 2 VD id plus VQ iq, and I need the torque. So torque is equal to power by omega mechanical speed, correct? So power is 3 by 2 VD id plus VQ iq by omega m. So on simplifying this, I'll get and for in electrical machines, there's a relation between the electrical frequency and the mechanical frequency, that is omega E is equal to P by 2 into omega m, where P is the number of poles on the machine. This is an empirical formula that has been defined. So I substitute it here, omega E will be there. So I'll get torque as 3 by 2 into P by 2 into lambda d iq minus lambda q id. So this thing is valid for all kinds of electrical, like alternating current machines. In our specific case, I'll substitute lambda d as this and lambda q as this. So on simplifying, I'll get 3p by 4 into this, I'll get this as the torque. So since I need to model this permanent magnet synchronous machine as a DC motor, in my controls I'll put ID as 0. Like I'll make sure that ID remains 0. So torque will come out. You can see that this is similar to this form. This and this are quite close. So now that we have established what the formula for torque is, now we can. Any doubts till now? So now we can start building the control. So why do you think we need to control the speed of the motor, speed and current? No, but it's a permanent magnet, flux is constant. Okay. So what happens is, now mostly these motors are permanent magnet motors are used in factories where it's now all automated. You use robotic arms and all. So you use it mostly. So when you're tightening a nut, if you do it more, your chances that will break the joint. So I need that to be controlled. So that's the main reason why speed control was developed. So first, this is the basic unity feedback controller, and this is the gain. So in this, for this whole thing, that I'll get the gain as y of this r of s equal to g of s 1 plus g of s. So for this controller, I'll get this as the gain. So my aim is, there will be a reference speed and there will be the speed of the motor. So my task will be to reduce the error between the reference and the output speed. So there will be some omega reference, and this will give me an output omega, and this will be some transfer function t of s. So this will give me the difference between the reference and my output speed, and I will try to reduce this difference, and I'll use a transfer function such that this gets reduced. Same for current. There will be a current reference, there will be output current, and I'll do the same thing. So we'll use a PI controller, that is a proportional integral converter. For a PI controller, the transfer gain is so this is what the PI block looks like. This will be R of s, Y of s. So my output will be this R of s times this function. So can I erase this? Where? Oh, sorry. So I'll assume there is no loss in the motor, that is resistance, all resistances are 0. So I can represent the stator winding like a simple inductance. It will be something like this. This will be a basic diagram of your stator windings. The star connected, A phase, B phase and C phase. You'll have 3 inductors in star. So my controller will, for current, thing like this. Controller, my total transfer function I. Since these two blocks are connected in series, I can just multiply their gains, and then it becomes a simple unity feedback. For that, gain is like that: g of s by 1 plus g of s. So it will be simplifying this, you'll get what I'll get finally on simplifying. So for a general second order system, any general second order system, my transfer function will be something like where zeta is the damping ratio and omega n square is the natural frequency of the system. So when I compare with this, I get what I'll get. Want the oscillations to die out fast. So I would want my damping ratio to be small. So based on my needs, I'll decide fix some damping ratio and natural frequency. So based on those damping ratios and natural frequency, I'll decide my Kp and Ki. So I'll get then based on this, I'll design this controller. So this is the current control. Now I would want to control my speed. So for speed also, I'll use a so for this is I wrote the equation for torque. But you also know that torque is equal to moment of inertia into angular acceleration, or that is omega dot, where omega is the speed of the angular speed. So when I take this is in time domain, when I take it to frequency domain, so this differentiation will be just replaced by S multiplication. It's similar to multiplication by S. You'll learn this in signals and systems. So. And into J of omega. So I'll equate these two. So my torque. So my omega will come out to be 3 by 4 into P into lambda m IQ by S. So this is what I will get as my omega, omega. So in this I will replace So this is mechanical speed. I need the electrical speed. So omega E will be just P by 2 times that. I'll take 3 by 2 into P by 2 square into lambda m IQ by S. I'll just put this P by 2 square as another number. 3 by 2 into n square lambda m IQ by S. So I'll just put 3 by 2 n square lambda m with j terms. So this is my reference speed and this is my output speed. So when I write the transfer function for this controller, I'll get omega by omega ref is equal to So this will be my transfer function. So when I simplify this, I'll get again comparing it with this transfer function, I'll get omega this is what I'll get. So based on my necessities, I'll fix omega n and zeta, and then decide my ki and kp. That will be so I'll fix my ki and kp. So this was my current controller and controller. Now we'll package everything into one full controller that will look like Can I erase this? So within this block you will have this whole transformer. So this is what my final controller will look like. The motor is running. I'll have some speed coming here. If I set I'll input a reference speed. Based on this, I'll get a reference output current, which then again will produce a voltage reference. And this, then I'll get two voltages, one for VD and VQ. I convert it into the ABC frame. So I'll just do the inverse of that operation that I had explained earlier. After this, I'll get voltages, reference voltages VA, VB, VC. I'll pass it to a PWM generator, and from that I'll get a sinusoid output, so that the RMS values are VA, VB, and VC. So from that, the motor will be drawing some current. I'll feed it back to the current controller. So this is what my control looks like. And that's how you control a synchronous motor in a way similar to that of a DC. Any doubts? That's it. If any doubts, you can contact me. My name is Aditya Rangarajan. No, so this is what I did in my internship in IIT Bombay. Like, this was one part of it. My task was to design windings for a synchronous motor, and like there's some prof had come from a foreign university, he was giving a talk on it, so he was talking about this.